In today's lesson, we are going to talk about complex numbers. Now, complex numbers, we want to talk about kind of on a more general or broader scope. So we're going to talk about the properties of complex numbers. So normally when we talk about a number system, a lot of the numbers we've been working with are real numbers. And then real numbers are divided between rational and irrational numbers. Complex numbers include all the real numbers, but they also include what we call imaginary numbers. So we are including more possible types of numbers when we're talking about complex numbers. So the complex number system contains all real numbers, and then in addition to that, we include imaginary numbers. Now, anything that applies to real numbers will also apply to complex numbers with maybe a very slight caveat. So, addition, subtraction, multiplication, and division of complex numbers obey the same rules of arithmetic that hold in the real number system. There is just one exception, and that's with the exponent laws. So exponent laws will hold for integer exponents, but not necessarily for fractional exponents. Now we worked a little bit with fractional exponents. We talked about how we can rewrite fractional exponents or rational exponents as a radical. And the reason why this becomes an issue when we introduce imaginary numbers into play here is because with imaginary numbers, you know that there are certain places where if, let's say, you have something raised to the 1/2 power and it's negative, we know that that should be an imaginary number because that's the same as the square root of a negative number. But there are some instances where the exponent laws are not going to hold simply because we are working with rational exponents, and with rational exponents, there are some instances where the exponent laws would effectively get rid of some of the very important aspects of imaginary numbers where the square root of a negative number is equal to I. So let's talk about the imaginary number. So the complex number system contains a number that's denoted as I, such that I squared is equal to -1. Another way to put this is I is equal to the square root of -1. Now every complex number can be written in standard form a plus bi, where a and b are real numbers. So a plus bi is equal to c plus di if and only if a is equal to c and b is equal to d. Now because all real numbers are complex numbers, you can still write it in this form a plus bi. It would just be that b would be equal to 0 if there is no imaginary part to it. Now when you're going about simplifying complex numbers, you want to always get rid of negatives under the square root, and you want to simplify radicals as much as possible, just like you have done in the past. So for example, let's say you have the square root of -36. Once you see a negative under a square root, you can go ahead and take that square root of -1, which is equal to I, and write it outside. So this is I times the square root of 36, and then simplify the radical. So square root of 36 is equal to 6, so this is I times 6, or in other words, 6I. For the second one here, we have the square root of -24. So we can go ahead and see that that -1 is under the square root, so we can go ahead and take the square root of -1, which is equal to I, take that out. And then let's simplify the square root of 24. So you want to break this down, since it's not a perfect square, you want to break this down into factors where one of the factors might be a perfect square that you can take out. So we can break this down into 4 times 6, because the square root of 4 is equal to 2. So now I can bring the 2 out. So this is 2i times root 6. Okay, so that's simplifying complex numbers. Now when it comes to adding and subtracting complex numbers, you are going to be adding and subtracting like terms. And by like terms, it's going to look just the same as like terms in algebra. So if you have 3x plus 7x, that would be equal to 10x. Now when you see an I in there, it works the same way, but just know that I is not a variable. It is, in fact, the imaginary number I. All right, so here in example 2, we have 5 plus 3i plus 1 minus 7i. So we're going to go ahead and combine like terms. So the 5 and the 1 are like terms, so we can add those together and get 6. 3i plus -7i that's equal to minus 4i. So this is going to equal 6 minus 4i. All right, in the second one, this looks a little bit more complicated. 6 plus the square root of negative 20 plus 4 minus the square root of negative 12. So same as before, you want to simplify any radicals as much as you can before you start trying to add and subtract. So let's work with the square root of negative 20 and the square root of negative 12 and simplify those as much as we can. So since both of them have a negative under the square root, I can go ahead and take the square root of negative 1, that's equal to I, and bring it outside. So this is 6 plus I root 20 plus 4 minus I root 12. Now, we want to simplify those radicals as much as possible. So the square root of 20, we can break that down into 4 times 5. And square root of 12, we can break that down into 4 times 3. And after we've done that, now we can take the square root of 4. So that would be 6 plus 2i root 5 plus 4 minus 2i root 3. Now we can see what like terms we have. So we can add the 6 and the 4 together to get 10. But the 2i root 5 and the 2i root 3, we are not going to be able to combine those two together because one is the square root of 5 and one is the square root of 3. You can only combine them if they are both the same thing under the square root. So we can just write this as 10 plus 2i root 5 minus 2i root 3. All right, so that's adding and subtracting complex numbers. Next, we're going to talk about multiplying complex numbers. So when you're multiplying, you would multiply like you would any other numbers, and then if you have any I squareds, you want to simplify. If after simplifying, you can combine anything else, you should do that. So example 3, we have 8i times negative 3i. So multiply just like you would anything else, so this would be equal to negative 24i squared. Now we see an I squared in there. I'm going to change that to negative 1. And now I have to multiply again, so that becomes positive 24. Let's look at the next one. This one looks like we have to do some distribution here. So 5 plus 7i in parentheses times 3 minus 4i in parentheses. So I'm going to do 5 times 3, so 15. And then 5 times negative 4i, that's negative 20i. Then 7i times 3, that's 21i. And then 7i times negative 4i, that's negative 28i squared. Now we can combine the negative 20i plus 21i, and that becomes just 1i. And then that I squared, I'm going to change to a negative 1. All right, multiplying the negative 28 times negative 1 gives me plus 28, so this is 15 plus I plus 28. And then 15 plus 28, which is equal to 43. So this is 43 plus I. Now we've talked about I squared, and we can see that as you multiply and it gets more complicated, you might actually end up with I to a higher power than just to the second power. So let's talk about what happens when I gets raised to higher powers. So I to the first is obviously equal to I. I squared we know is equal to negative 1. What happens after that? I to the third. Well, I to the third is the same as what? I squared times I. We know I squared is equal to negative 1. So this would be negative 1 times I, which is equal to negative I. Okay, I to the fourth then. Let's think of this as I squared times I squared. We know I squared is equal to negative 1. So negative 1 times negative 1 is equal to positive 1. All right, I to the fifth. This is the same as I to the fourth times I. I to the fourth we just found is equal to 1. So this is equal to 1 times I, which is equal to I. So up to this point, we've seen that this goes I, then negative 1, then negative I, then 1, and then it's back to I. And then what happens next? I to the sixth is the same as I to the fifth times I. So now we end up with I times I, which is I squared. So you end up with negative 1. So you can see that this actually ends up cycling through these 4 values. So we call this a cycle. So the powers of I form a cycle. Any power of I must be one of these four values: I, -1, -I, or 1. So if you are trying to find higher powers of I, such as I to the nth power, what you can do is you can divide n by 4, and if the remainder is 0, then it's equal to 1. If the remainder is 1, then it's equal to I. If the remainder is 2, it's equal to -1. If the remainder is 3, it's equal to -I. So for example, for I to the 5th, you would take the 5 divided by 4. You would end up with a remainder of 1, and a remainder of 1 means it should equal I. And this works for higher values as well. So if you have I to the 30th power, you can do 30 divided by 4. You get a remainder of 2, so that's equal to -1. Let's look at an example together. So I to the 54th power. So take 54 and divide it by 4. If you divide that by 4, now you could do this on the calculator. The only issue is we really need to know what that remainder is. Typically on the calculator, it gives you an answer in decimal form, so it won't give you the remainder as just a number. It will be the number over 4. So when you divide 54 divided by 4, you get a 1 up on top times 4. You get 14 divided by 4. That's 3. 3 times 4 is 12. 14 minus 12 is 2, so the remainder is 2. So if the remainder is 2, that means that this is the same as I squared, which is equal to -1. All right, so we've talked about adding, subtracting, multiplying complex numbers. We've talked about different powers of I. Now we're going to talk about dividing complex numbers. So if there is an I in the denominator, you always want to get rid of it, either by multiplying by I, both the numerator and the denominator, or by multiplying by its conjugate, also in the numerator and the denominator. If, for example, you have a plus bi in the denominator, you would multiply by the conjugate, which would be a minus bi. So you would multiply top and bottom by a minus bi. Now you only have to do that if you have both a part a and a part b in there, a plus bi. If you just have I in the denominator, you just want to multiply by I over I. That's simpler, and it'll be less simplifying you have to do later on. So take a look at example 5. We have 5 over I. So here's an example where you just have I in the denominator, so you want to multiply both the numerator and the denominator by I. Our goal here is to not have an imaginary part in the denominator. All right, so multiplying this, we have 5i over I squared. Remember, I squared is equal to -1. So 5i divided by -1 is equal to -5i. All right, now the second one, we have 10 over 2 plus I. So this is the a plus bi form where you have to multiply by the conjugate in both the numerator and the denominator. In this case, the conjugate would be 2 minus I. So I have to multiply both the top and the bottom by 2 minus I. All right, this means there's a little bit of distribution going on here. So 10 times 2, that's 20. 10 times -I, that's -10i. And on the bottom, we have 2 times 2, that's 4. And then we have minus 2i plus 2i, which cancel each other out. And then minus I squared. Now, anytime you see an I squared, remember you want to replace it with -1. So on the bottom, this becomes 4 minus -1. All right, and that becomes 5. And 20 minus 10i all over 5, we can actually simplify that a little bit further, and that becomes 4 minus 2i. Okay, and as this relates back to what we've been doing so far in this chapter, we've been talking a lot about polynomial functions. How do you factor polynomial functions? How do you find the roots? How do you use that to apply to rational functions? And so complex numbers, when we're talking about when you have solutions that are non-real solutions, but they might be complex solutions, we actually know that if a plus bi is a solution of a polynomial equation with real coefficients, then its conjugate, a minus bi, is also a solution of the equation. So just relating this back to everything that we've been doing up to this point. If you know that a certain complex number is a solution, you know that its conjugate will also be a solution.